Mickey gave us a broad overview of a lot of issues associated with climate change. I want to bring this home, in a sense, for us to a very specific issue. A lot of what we're here talking about is motivated by climate change. Other parts of it are about just more sensible energy management and that sort of thing. And what I'm going to try to accomplish in a few minutes is to maybe make you aware a little bit more than you might be of how closely tied our water supply, you know, the water we drink or the water that goes into irrigation, is to our energy system. And then I'll end up with a couple slides to tell you some gloom and doom stories about what happens under climate change. Typically, I'm a guy who focuses a lot of my science on the water cycle. And so typically a water talk will start out with a diagram like this, which shows a big, Mickey referred to it, a big system with evaporation and precipitation and runoff and all that stuff going on. And it's described as a hydrologic cycle. But if we're going to talk about this water energy nexus, it's more useful perhaps to think about the human part of it. As Mickey said, you know, the climate system, the water system are no longer just about nature. Humans have got a big place in them. So this diagram sort of gives a sense of what happens and what we have to do with water to use it for irrigation, for drinking water, for residential uses, commercial, industrial. You grab the water from some source. You have to bring it to wherever you're going to treat it, which often involves pumping it up over mountain ranges and that sort of thing. You have to distribute the water for the various uses. Then you have to collect the wastewater that comes out the other side, treat that water. If your community is a good steward, environmental steward, maybe you grab some of that and recycle it and use it again. And then finally, you have to get rid of it. And for most of us in this world, you know, you might think that it goes into not a source but a sink, but really it goes into somebody else's source in most cases. So that's why I call this a cycle, in that, you know, we grab water from one end, manipulate the tar out of it, and ultimately dump it into someone else's source, so the whole cycle begins again. I just put that up there. Just now I've added the energy requirements for those various steps on this diagram. And there's a lot of numbers up there and that sort of thing. There are two things to get from the diagram. One is that at each step of the way, it requires energy, often electricity. And I haven't got a number in the end use box because of, you know, how much energy you dump into the water at that point depends on how you're going to use it. But at each step of the way in the other boxes, you're talking about dumping in energy. So, and there's a bunch of numbers, but the key number perhaps is down at the bottom where you add it all up. And what you find is that, in our country, let me put it that way, the total amount of energy that goes into, you know, a glass of water, well, actually 1 million gallons of water for you to use, range is from somewhere between 2,000 and 20,000 kilowatt hours per million gallons. And I was back there sort of pecking away this morning to make that somehow sensible. And what it amounts to is that at the 2,000 kilowatt hours per million gallons level, it means that, you know, any water that you drink or irrigate with or otherwise use has an amount of energy, often electricity, put into it that would lift that water now 500 feet or so in the air. Okay, at the 20,000 level, it's almost a mile in the air. So the upshot is that, you know, our water supply is a huge demander of energy. And so our water supplies are very much tied to that. I'm going to push on just to give you some examples of how that ends up working out in California. In California, our water supply system within the state draws about 19% of all the electricity that's used in the state. Just to keep it running, just to move the water around, treat it, distribute it, capture it after it's been used, and treat it again and dispose of it. And as you can see there, about 30%, almost a third of the natural gas demands are dedicated one way or another to our water supply system. So California's water system is the largest single user of water, of electricity in the state. As you can see there, the amount of electricity that's used to deliver the residential water to Southern California is equal to about a third of all the electricity that's used in Southern California. So again, when you think of water supplies and the like, it's the big gorilla in terms of energy demands, and especially electricity demands. You can see there 90% of the electricity used on farms goes to pumping groundwater for irrigation in California. And finally, during the bad old days of the energy crisis in the early 2000s, when there were rolling blackouts and that sort of thing going on, everyone was trying to figure out how to cut our electrical demands. And a number of studies came out that made a very convincing case that the money spent to reduce electricity demands by traditional methods was less economical. It gave you less bang for the buck than the same money spent to reduce water demands. And it's because of all these, because of the major role that water in the state plays in the overall energy demands.